Yeah, welcome to my talk. Wait, the mic, is it working? Yeah, now it's working. So I do not like hearing myself over the speakers, but I think for the next like 45 minutes, I need to get used to this. So this is about an approach to integrate like a machine learning, like a deep, actually it's a deep learning, machine learning framework into the D programming language. So this was primarily developed by Joe, who's sitting over there, and me. So we've been like working.
Mostly you.
Okay, so he says it was mostly me. I say I had some good feedback that actually made the code better. So this is about like an integration of this library. And so the talk will progress in kind of like 3 stages. So the first stage, I think, will be a rough one for most of you, because it will be like math. So I will go through a simple example that shows a simple machine learning problem, so like all of its math, the mathematical formulas and everything. I think this is useful because then you can actually see like how the math is actually translated into code. So you should somehow see this relationship then later on, I hope. Let's see. And it's also kind of important if you want to write your kind of like solve your own models and implement your own models, because at some point you need to do this transition. Or let's say even if everything is set up perfectly, even then you will benefit from actually understanding what is actually happening under the hood, because then you can tune it and make it work better, I think. So this is the first stage. The second stage is then actually more looking into this MXNet library. This is the deep learning library that is going to be that we integrated essentially, and so it's also looking at other frameworks. So why did we choose MXNet? Because I'm sure nobody here has heard about MXNet. So anybody heard about MXNet? 1, 2, 3, yeah, more than expecting actually. So it's actually more popular than expected it to be. Okay, so and the final one is like only about like, you know, showing some code, how to actually use it, and even a demo. Let's see how that works out. And yeah, so let's get started. So remember, we're going to start with the math. So I try to make it simple. I think it won't be. Sorry, it's unfortunately hard. I have some pictures, so I hope that I do not lose you. So, but feel free at any point, just ask a question to clarify, because I don't want to lose you. So the more I get like across, the better, right? So I said we're going to talk about like logistic regression, which is a bit of a misnomer. So because in machine learning, regression problems are usually when you're trying to predict a scalar, like a real value. So this one here is actually classification. So I don't know why it has this name. I think you can figure it out why it is like that. But this is actually classification. And actually I'm restricting it to binary. So meaning you get some kind of like labeled input data, and you're like supposed to predict the label. And the label will be like either, let's say it's an A or it's a B, it's an apple or it's an orange, or it's spam or ham, right? You know these kind of like problems, right? So there's this one slide that just to like, I don't forget, right? There is some math ahead of us, and I mean, so I guess it can be hard. I hope it isn't too hard. But you have to somehow like get through this. I think there is no way around it. So you somehow have to like learn this underlying language that is used to describe these problems. All right, so let's start. So I'm building the model kind of like inside out. So in the very inside of this model, there's this notation. So this is mathematical notation. So all it says here, I'm defining some vector. So think about it like a real, let's say a fixed size. Let's say n, 1,000 or whatever, right? And this is a vector, and it represents your sample, your example data point. So let's say you get some representation of the email, the text as numbers. And this is what this vector, this vector xi actually is. And then you have what is called here theta. These are the model parameters. So you are combining these input data somehow with some model parameters to actually come up with a prediction, with the label. So what should this be? Is this mail actually spam or is it ham? And this t, this little t above there, that is now a mathematical notation for representing the dot product. So on the next slide, I will give you somehow like a feeling of what this actually does. And maybe some of you, so some people that have like more or have experienced some math during their life, they may already kind of know what this kind of looks like. So because if you look at it, if you just imagine there's here something like, you make it into an equation, let's say this equals 0, then you have what is called a hyperplane. So hyperplane looks like this. So essentially this is our theta, that's the normal vector that is perpendicular to this hyperplane. And now essentially you kind of can already see this like classification thing, you know, everything that is to the, what is it, like for you, to the right of this, it's going to be labeled like the one label, I don't know, let's say apples, right? And everything to the left of it, these are going to be the oranges. So this is why we have this notation, why we express it like this. So and what this dot product now does is, essentially it combines this theta and this xi together to actually give you a real value, meaning it could be any number between like -infinity or plus infinity. So because the x could be like way over there, right? And it could be, technically you do not know where it is, right? It could be everywhere. And so here you would actually get then now minus infinity. So the problem now is we are going to reformulate the problem further, because I'd like to represent this more like in form of probabilities. So currently we get this number between like a -infinity and infinity, and you do not know much about this. So that's why we are going to introduce the logistic function. That is also sometimes called the sigmoid function. So you may know it under this name. The logistic function is actually a bit more general because you have some parameters that you can actually choose to change it, essentially. And I guess most do not see, like, what does this mean, this formula? I do not see anything what it does here, right? Even for me, right, when I first look at it, so what does it do? So, and when you like just plot it, you see what it does. So essentially here on the x, we have now our, like, the input of the dot product, and all it does, it maps it into a range between 0 and 1. That's what it does. So let's say here in the very middle, let's say 0. 0 would be like 50%, or like a half, essentially. And so that is, you know, when it lies exactly on the boundary, then you do not know. So you do not know, is it actually an apple or an orange? You do not know. And sometimes, you know, you break these ties somehow. I mean, actually, it's like more like a not so much of an important thing. Okay, so now we can like apply this, right? So we can plug our like dot product into this equation here to actually turn this now into like a probability. So meaning now we would essentially return, we would here have some like -infinity till until infinity value, and now this gets wrapped into like a probability. So meaning what you somehow could expect is that the farther away the point is from the hyperplane, from the separating hyperplane, the more certain you are that this is actually an apple. Because if it is very close to the hyperplane, then you don't know. So because maybe it is just by accident on the wrong side or whatever, right? So there's also a bit of other notation here. I think it's not too important. So here I made this distinction of like with the semicolon to actually say, you know, this is actually my thing that I plug in, and this is what the function is parameterized in. So this is actually the thing I'm trying to learn. I want to find a theta such that my data is nicely separated by this, essentially the theta is the hyperplane, specifying the hyperplane, right? All right, and now there's one other thing that you need. So now we have kind of said like how to map an observation, a training example into a probability, and now you have to somehow combine this probability with the let's say training data. And that is what this cross-entropy loss does. And so the idea here is, again, I guess from the formula, if you do not work with it regularly. You do not see what it does. So I tell you what it does. So this is, the summing here is like summing over the events. In our case, we only have like this labeled. So either it's a 1 or let's say it's a 2. And this is just summing over the events. And essentially, we are now here comparing these probability distributions. So this one here will be our prediction. This will be now, essentially, you can think about it like a vector. So either it will be like the first probability here, P1, that is, let's say, the probability that we classify, that we say this is an apple, and that it is not an apple is just 1 minus that it is an apple, right? So because these probabilities have to sum up to 1. That is one requirement, otherwise you wouldn't have probabilities. And here are just our observations. So this would be a vector where essentially when you observe it, you say, you know, if I see an apple, then I say it's 0. So let's say here it's 0 and here it's a 1 to like denote that it's an apple. If it was an orange, you would make the 1 first and then here the 0. So you somehow translate your input data into a probability distribution, but it's like a strange one in a sense because, you know, it's very certain. So why would you introduce this? And the reason to introduce this is only to like have here this way of comparing these probabilities. These probability distributions. So because what you now want to do is you make predictions of what the probability distribution should be, and now you compare it with what you have seen in the training data set, and you want to match this. So you want to have as little loss as possible. So essentially you want to minimize this. So I have a picture for this one as well. So here, so there are technically now two terms, right? So x is the probability of predicting that it is an apple, and 1 minus x is that it is not an apple, let's say an orange, I don't know, right? And so if we follow now the green line, so if we plug in something very close to 1, meaning we see an apple, and we actually say it is an apple, because we are close to 1, then we actually have almost no loss. I think it's 0 here, right? So at 1 it should be 0. But if we are less certain, you see that you get more loss. And of course, you know, in the examples you see it is an apple, so you want to push it here for this very observation that you've seen. And for the other one, just symmetrical, the other direction. All right, and now comes the slide that I was kind of like sweating over. So do you say it like this? So I wasn't sure whether I should include it. So because it's a heavy one, and I will show it anyway. I just want to tell you that, you know, you could, maybe I should check out your reactions when you see it, right? So this is the slide. So actually it's not complicated math, right? But if you're not used to it, it looks very complicated. And for me it's just, how do you say, I couldn't help it. I wanted to have the slide because I think it is important to understand the math that is behind it. Because I think if you just apply it, if you just use some tool, I think you will have a hard time. So I think it's always better to like, have this kind of like deeper understanding of the things. And so here I'm essentially just simplifying this formula because I find it like it kind of explodes, and it's not nice to look at. And I will go through this now. So I hope to like get very many of you to like join me in following through this. But actually, I'm now just rewriting the formula to make it more like compact. All right. So deep breaths. Let's go. So this was our cross entropy loss, right? So this is what we said. And now the first thing I did is we talked about this one-hot encoding of the observations here. So I'm now representing this with an indicator function. So meaning if the label was actually, let's say, y1, then here there would be a 1. Otherwise there would be a 0, meaning this one here wouldn't have any effect, right? Because 0 times something is like nothing. All right, so this is the first thing. We're rewriting the indicator function. And now the next line is we are, how do you say, unplugging the sum. We are like making it explicit. So there are only two cases, right? Either it is this label, then I want you to have this loss here, or it is this label here, then it needs to be 1 minus, because, you know, as I said, these have to sum up to 1, right? That's the first thing that we do. And now we just plug in. So we already decided that our predictions are going to follow this like logistic function. So that's what we plug in here, and here we plug in just this logistic function again. So that is like straightforward, right? And now comes a nice observation that actually is not hard to see. So when you look at this logistic function, you can actually show that it has like kind of like a symmetry property. So meaning 1 minus the logistic function is actually, as if you say, the logistic function negating its argument. So that's a nice thing, because now we can, oh, I got rid of this 1 here. And the next thing, another last trick is that by now we haven't fixed our labels. And now I'm actually introducing specific values for the labels. So now when I set up the problem, I have to use these labels, but I do it for a reason, because the reason is then the formula gets simpler. So if you plug in, let's say that the first kind of label is actually called not apples or orange, it's a 1, and the second label is always denoted with a -1, then when you just see it, when you plug it in here, so let's say, where can I show? Here is where I put it, right? So if I plug in this y1 in this first case here, this won't do anything, right? It's just a multiplication by 1. And if I plug it in here, I actually get the minus here for free. Oh, not for free, I get it. And so now I can just have it here, which is more compact, right? So instead of like having these two, the sum here, I have it like more compact. So I like it to be this compact. Okay, and the last one, they are like kind of obvious when you work with these things. So minus the logarithm is just you can, how do you say, invert the fraction here. And so by removing the minus, you just get this one here, which looks again nicer. So this is now almost finished. So let's continue. So this is now what we finally have. So that is what we now did. I introduced this logarithm here from the cross entropy loss, and we made these reformulations so that actually we can put in the labels here. And now there's one thing. So far we have only talked about a single example. All this was a single example. It was one example with one label. That's why we are at I. So we want more examples, right? So we sum. That's the next step. You just sum over all the losses, and you get something like, I would call it the total loss or whatever. So usually you cannot make, or we could make distinctions in the sense of, we could say this data point is more important to me. Then you could introduce some weights, but usually you don't have this. So that's why we're just summing all the losses up. And this is what we now want to minimize. So we have all these losses collected, and the task is now to minimize this. Let me see, I think I have some further things that I did here. So this one is another transformation. Actually, it doesn't look like much. I think it is important though. So what I now did is, do you remember we used to have here this dot product? Essentially, we are picking one point and calculating the dot product with the parameters. And you can do it like that. But as it turns out, when you kind of like implement it, that's kind of inefficient. So all these kind of like operations, they are usually mapped to some kind of BLAS implementation. And BLAS comes in layers. So the first layer is, I think, vector-vector operations. The second layer is vector-matrix operations. And the third layer is matrix-matrix operations. And usually it is the case that when you go up in this hierarchy, meaning expressing your problem in a higher layer, that you get more efficiency. I think it's just because, they see more of the problem and they can like optimize it or tune the implementation better, right? And so what we're doing now here is essentially just this. So assume all of your examples are like now in a matrix and row-wise. So each row is an example, and theta is still a vector, so you're multiplying this. This is now a notation I introduced for like having the element-wise multiplication between this y, which is now also a vector. This one you apply now element-wise, so it's not a function anymore that gets a scalar as input, it gets a vector as an input. And this one here is the vector that is everywhere once, And this one again is like applied like on a vector, not like with a single scalar, but element-wise. All right. So, and again, we need to sum. This is now a vector, the vector of the losses, and we still sum over it, right? All right. So this is it for the math, right? So we are over with it, and you're all still here, so that's good. And so now I'd like to somehow like summarize a bit, but a bit like from a higher level. So what we have seen is what you need is data. And your data always needs to be like in a numeric form. And that you have to somehow do. Either it comes naturally, because let's say you're measuring something and that comes with numerical measurements, but it could be that you're working with text data also, right? Then it's not so clear like what is actually the numerical value of this. And so you have to do this. Somehow you have to put your data into numerical form so that you can actually start crunching these numbers, right? You need numbers to actually do this. Okay, and these things usually come in different forms. So they come in scalars, vectors, or matrices, or even like higher level than they use the general name tensor. So meaning, I mean, you could just think about it like an n-dimensional array, right? And so you can have as many dimensions as you want. So there's nothing restricting you. With data also comes another thing. There's kind of like a trade-off. Usually you want as much data as you want, because usually it doesn't hurt. I mean, it could hurt, but usually it doesn't. And you also want high-quality data. So meaning it can actually make a distinction whether maybe you don't have so much data, but maybe your data is like qualitatively better. Then actually it's maybe good if you have less data. So this additional data doesn't give you much. Okay, so this is data. We need somehow data. Next thing is we need these models. And these models essentially define a mapping from the input data using some model parameters to essentially your predictions. So somehow we define this functional mapping of what it should be. I should say here we only did like supervised learning. So in supervised you always have it like this, set up like this, meaning you have a model that maps this, and then you have an output that is your prediction, and your prediction is compared to what you actually see in the data, what you have like the labels that you have observed. There's also unsupervised, and where it is a little bit different, where you're only interested in like finding structure inside your data, of your data. Okay, and there are various, I mean, you can find like lots of models. There are very many different classification models for doing classification. There are very many different models for regression. And then like factorization methods is about factorizing your data into, how could I say, like abstract features. I mean, maybe I shouldn't go into this because that's not the point of the talk. And of course you have now these days deep neural networks, which are like very, very complicated models to actually solve like very hard problems. All right, and then we also need like a loss, because we need to say actually how do we are going to penalize the combination of the loss, how we're going to penalize the combination of our prediction with what we have observed. And there are again like modeling choices. So these three here, these are actually like, you can see they are symmetric, so these are usually regression losses. So meaning actually you try to predict a real value, and they are symmetric because, you know, it's bad in both cases. I mean, if you're not hitting the value, if you're to the, what is it for you, left of it, then that's bad. But if you're to the right of it, that's also bad, right? So you need to be close. Whereas with the classification thing, it's not like that. You know, if you're, it's only a problem if you're on the wrong side. You do not care how much you're on the like proper side, right? So this is here, these are like examples for losses you could use for these cases. You can see they are asymmetric, right? So essentially when you're on the right page, on the right side with your predictions, you do not want to penalize it. The loss should be 0, right? So that's what these losses do. All right, and then we have model parameters. So usually in this kind of like setting that we do now, this kind of like machine learning, it is that you update these model parameters. And you update them such that you minimize this loss. So you're walking over your data, and you now update the parameters such that the loss is like minimized. That's the basic idea, and that's always the case. These days, you also tend to have like very many parameters, so that you need to think about like distributing your parameters. It could also be that you're thinking about distributing your parameters because then you could like work on them like asynchronously, meaning you could have several workers that fetch the same, maybe not the same parameters, but at least they could fetch the same parameters, work on them, and then maybe some other worker fetches them and works on them, right? So this is how it is with model parameters. So let me continue with the optimization. So I said you have to update the parameters somehow, and basically all of the existing, or most, I think almost all, are using kind of like a variation of this gradient descent step. So the idea with the gradient descent is like, let's say you're somewhere in your surface of your function, you're here, and then you get the gradient. And the gradient has the property that it points into the direction where you could maximally increase your function. We are interested in decreasing it, right? So that's why we negate, which is this minus here, we negate the gradient. So we are actually interested in the direction that maximally decreases our function value, our objective value. And this is the basic form of the update. And just as, this is the old parameter, and the old one is like, go in the direction of the gradient, of the negative gradient, which points like in this maximally decreasing direction. And then there's this alpha, which is the learning rate. So the learning rate is always a bit special because there are no like, I would say there's nothing known how to actually choose this. So essentially, you do not want to make it too large, because if you make it too large, you're always jumping too far. So meaning, let's say you're already close to some minimum, and now you have like a huge learning rate, then you jump over it, right? And so you might actually not converge at all. So, but that is why you do not want to have it too large. But then you also do not want to have too small, because if you make it too small, you have too many steps to make. That is inefficient, right? So somehow you have to tune this, yeah?
Or what if you have some multiple minimums?
Yeah. So essentially, I think most of them, they converge to. So there are tricks actually to tune this, to somehow jump out of these local things. So yeah, I'm not telling here like the full picture. Yeah, there are ways to somehow like fiddle around with this learning rate to actually do this. And there is some paper that actually discuss this. All I'm saying, it is only like empirical. So there's no, so you can try it, maybe it works, maybe it doesn't, but it's like no hard, yeah, there's no good answer there, I think. For convex function, that's of course not the case, but yeah, usually with the advanced models, that's not convex anymore. Yeah, so yeah. So there are learning rate schedules. I think there was something that was popularized by this fast AI course, Leslie Smith, I don't remember his name, but he actually found kind of like a way to estimate a good learning rate for your problem. So, but you definitely need to look into this, like find a good learning rate, because it's like important, because it determines how quickly you're going to converge, right? All right, so now let's come to this MXNet thing. So MXNet is a deep learning library, and I think I just, like yesterday when I thought, on their webpage they say they mix symbolic and imperative programming. I think that's why they're called MXNet. So even though it's spelled MX, I think they said in the paper you have to say mix. So it's MXNet, and I think what they're especially proud of is that they have a good combination of symbolic description of your problem and imperative like executions. So the thing here is that when you look at TensorFlow, for example, it started out mostly like being strong in the symbolic area, and only recently moved into like supporting more like eager, I think they call it eager execution. So we get to this point later, I think. And then they have like a dependency scheduler. So the dependency scheduler just does the following. If you have like operations to perform, you need to ensure that all your inputs have already been calculated, right? You can only schedule or perform executing this operation when all of its inputs have like been computed. And this is just what this dependency scheduler does. And then they're very proud of having a a memory efficient and fast execution of these symbolic graphs. So the moment you have like a symbolic description of your formula, of your mass, then you can try to optimize this graph. And you optimize it for like being memory efficient because you may need to run on a GPU and it doesn't have so much memory. And you also want to execute it quickly, right? So these are the two things that MXNet cares about. All right, and here's one graph where actually you can now form your opinion. So I plotted here what is trending. I plotted actually 3 frameworks that are trending on Google, meaning people search for it on Google, right? So I extracted this from this Google Trends thing. So any ideas like the green graph, TensorFlow, yeah, that's TensorFlow. You can actually see like here, that's pretty interesting, right? So there was like a huge hype in the beginning. So there was some good marketing going on here, I guess, because everybody started looking at it. Or it was, I think, or it was just when they released it. I don't know. So, but this is like end of 2015 when actually it was open sourced. So what about this one here, the blue one? Any ideas? No. Ah, that would be good. If that was MXNet, I would be happy. So there's PyTorch. So I think Facebook moved this Torch library. I think they even developed a Torch one. I don't know for sure. And I think around this time, like PyTorch took off. And these are actually competing ones in the sense that PyTorch was all about more focus on this imperative way of building these models because it's much more productive. You can compare it to like, you know, when you're like trying something out, it's much simpler in a like interpreter because immediately it tells you, yeah, there's something wrong compared to, let's say, when you compile it and then after, you know, DMD takes some time and then when, there's something wrong and then you need to fix it and then you run to the next error. So TensorFlow is originally more like of the like compiler thing. They want to like heavily optimize the graph because they, you know, this graph will be executed over and over again. So it's actually good to spend some time there. Okay, so blue one is PyTorch. Yeah, this one here, it's MXNet. So what you actually see, people are not searching for it. And I think it's not because there are no questions about it. I think it's just not used very much. So here you have it. It's actually a reason why maybe you do not want to use MXNet, right? Because it seems nobody else is using it. All right, so why nevertheless did we choose to go with MXNet? MXNet has one property that sets it apart from all of the other libraries. It is that it exposes all of its functionality through a C API. So with the other frameworks, usually you cannot access all of the functionality. Usually you only get essentially the execution of the graph, but you cannot make gradient update steps and calculating even the gradients. That usually doesn't work. So this is like a good reason. So if you want to do all of your training and predicting in D, then this is, I think it's maybe one of the only options if you want to use some already existing framework, right? So you could do both prototyping and production code in D if you integrate it. And of course, you can use your existing D skills, right? You do not have to learn Python, which would be the thing you would need to do if you want to do like machine learning, right? Python is the one that is being used. Yeah?
There is one more reason for using MXNet. It's endorsed by AWS, for an example.
Right. So I didn't mention, but yeah, I know. So you are referring to that.
Thanks.
Amazon kind of like.
Yeah, it's endorsed by Amazon. So if you're running your stuff on Amazon, MXNet is probably the way to go.
That is true. And actually, I was hoping to see it here.
Yeah.
Unfortunately, it didn't. So I don't know. So it could still be that it's like still. So it has now some like more major backup from like companies, even like. So you could somehow see that all the other companies are somehow like joining forces to actually build something similar to TensorFlow because TensorFlow is quite strong.
But the reason for this kind of graph with MXNet is because both TensorFlow and PyTorch are in the Python world, so much closer to Python, and at the moment Python is de facto standard for data science. True,
but there's also like a Python interface for MXNet, and that's not a bad one, I think. It's sufficiently good, so you could also do it there. Yeah, but that's true. So yeah, it has some support from Amazon, and yeah. All right, so underneath, like almost all, I would say, of these frameworks, they use the same thing. So there are like BLAS implementations that are tuned for your hardware, and so there's one from Intel for your Intel CPU, there's Apple for Mac, I guess. Atlas is like an open source thing, they auto-tune these routines, and OpenBLAS is another implementation. There's also CUDA, so if you want to run it on graphics card, you would use the CUDA implementation, or here this is especially for deep neural networks. So they also have support for this. There's also something that I found recently. There's Open Neural Network Exchange, which is a repository where you can find pre-trained models. All right, so I think I should speed up a little bit. So we have this divide between symbolic and imperative, and I think we already have talked we spent quite some words on this. So you want I think you want both, because the symbolic one is one that you know that will be optimized, that is like efficient and everything, whereas the imperative one is good for like developing your model, debugging it and everything like that, because it's annoying when you define your like very complex model and then at some point you're actually going to like use it and then it says there's something wrong with it, right? You want this feedback very early. So in MXNet you can define your symbolic network, bind it with values and then execute it. You get the like symbolic approach, or you can get the imperative one, which is like you just schedule operations on n-dimensional arrays and they would like be scheduled and then evaluated right now. The MXNet API, you could divide it in like subparts. So there's one part that actually exposes you an interface to access the predefined symbols, what they call atomic symbols. And then there's an API to work with symbols, I mean all of the symbolic part. Then there's a part to work with the imperative one, that's the n-dimensional arrays. You could think like tensors, right? So that's the same thing. And then you have an executor that binds these things together to actually make passes over these networks. There are also parts now recently introduced, I don't know when, maybe a year ago, so I don't know for sure, about autograd. They call this autograd, which is similar to the PyTorch way of calculating gradients. So it's more that you have a gradient tape and you perform your imperative operations, but while this is being performed, it keeps some tape to actually store information to calculate the gradient. So they also have this. It's not integrated in the MXNet, but it's like one could, right? It's like maybe a handful of functions that you need there. And there's also a key value store. So the key value store is actually to implement something like a parameter server. So they are very focused on this architecture. Parameter server is essentially where you have your model parameters in a parameter server, and then you have your workers, and they like communicate with the parameter server to do these updates, right? There are many more. There's a profiling API and image API, dataset API, but yeah, these are the basic ones. So here's now an example. So this is here I'm defining a symbolic network. So here, this is this X. This will be my feature matrix. That will be the matrix that will contain the data points. This is my Y. This will be the labels for each of the data points. Here is my parameter, which is this W. And now I'm actually like defining this fully connected means essentially matrix multiplication, right? So this will be executing this X times W. And here I need to give the num classes because it wants to know how many columns this will have. I don't know why, maybe for some optimization that it needs to know this. All right, and then you have the softmax. So this is actually a generalization of the logistic function, which does multi-class. So remember, we only had like 2 labels in our examples. You can extend this to support like as many labels as you want. And then you would use the softmax function, which is just a generalization of the logistic function. All right, so now we have kind of defined our model and our loss. Loss is also part of here, so that's why it is called output. So they use this cross entropy also inside there. All right, and now you define the context. Context is actually where you're going to carry out these computations. So usually it's, in this case here, the CPU, but you could also pick like a GPU that you have on your machine, right? And then you define a batch size because you iterate only in batches over your data. And now you're actually now starting to create here an actual value, an actually ND array. And that is the ND array that will hold your your examples, your training examples. And it will have like batch size times number of pixels. I think here it's images. So each image has a fixed number of pixels. And so for each row, you get this number of pixels. All right, and here you have your label variable. Then you would initialize your model parameters. So to 0, that's what we do here. And you also provide some storage where to put the gradient. And then you bind the executor. That is, you have to pass it in this order. So first the values for this one, then this, then this. So this is what we do here. So we give it a context. We give it the symbol that we like to bind. We give it the arguments. This is what we just built. And then we give it some storage for the gradients, and then here what to do with the gradients, because you could either say, calculate me a gradient, don't calculate me a gradient. And here this is auxiliary storage that we don't need here, that's why it's empty. So now we have bound this executor, and now we can run over it. So you copy your data into your matrix, into the matrix essentially, and then you make a forward pass, which would just do the predictions, and the backward pass would calculate the gradients, and then you make here this gradient update step. Actually, you can call here again a symbol, but I didn't do here. So this is now the imperative way of doing it. You could also directly call a symbol here, which would maybe be more efficient. So that is the so that is somehow the interface, and so yeah, we are like summing up already. So I think still DMXNet is still like in an early development. So I mean it's 0 something. I think we will have a 1-point release soon. I mean it depends on what you want to include there, because then we are not allowed to break anything anymore, right? So then you can only add on top of it. We are only primarily targeting Linux. So that is our platform that we use. I think it's usually not a problem to support any other platform, because essentially MXNet does all of the work, right? So MXNet works on macOS, Windows, and whatnot. We have many unit tests and a single integration test. That is actually, so the code was copied from that integration test. So that actually is performing prediction on the MNIST dataset, which is hand digit recognition. So one could add more there, definitely, if you want to. And we have documented it. So actually well documented, I think. So that's good, I think. All right, now I would switch to the demo. I don't know like how much time that's not a good thing, right? So let's try reconnecting. So now I'm cloning DMXNet. Let's see whether it works, right? Because it just was complaining about, yeah, maybe you should just have a 5 there. I have glasses, I'm almost blind. So I only have 5 minutes, but I guess we can make it work in like 5 minutes. So we are cloning the repository here. We are now running the tests, building DMXNet, running the tests. Underneath it's using this version of MXNet, and here it starts predicting MNIST and achieve this kind of like accuracy. So that is this, but I have a little bit more of a demo. In the interest of time, I won't go through the code. I will just show you the output, I think. So what you can do is you can download like deep neural networks and just use them, right? Which is what I'm going to do now. So here I defined all of this like code. And now we can actually now make it predict something. So this model is built based on the ImageNet dataset and like this VGG19 deep neural network. So let me download the picture. Let me show you the picture. It looks like an innocent seagull. And let me now run this thing. So here I'm loading the network, I'm loading the parameters. And now it's telling me it's a sandbar or seashore. Maybe that's not right. So actually I looked into the data set. They do not have the example of a seagull. So that's why they cannot predict this, because they have never seen a seagull. So let's do something that they have probably seen. Let's try what I have here. I have another thing. I think it's let's see what it is. I think it's Yeah, I don't know what it is. So actually, either it's a leopard or it's a geopard. So there are some like distinctions. Let me run this one here with this picture again, loading the network, and now it says it's a leopard. So it's like with 35%. It says, you know, of all the labels that I know of, with this probability, it's a leopard. And then we can also have it's very good with beers for whatever reason. So I didn't know that maybe you can tell me whether it's actually right. So all I know is that if you run this here, this is a bear, right? Looks like a bear. And it actually says it's an American black bear. I didn't know this. So maybe it even isn't, I don't know, but it's very certain. So it gives it like 50%, right? So I don't know. All right, so this is the demo. Let me switch back to the slides. Yeah, Outlook. So there is some cleanup to do because this library started out as a D1 library. I have to watch the time. Started out as a D1 library, and there's still some artifacts in the code where you could actually see, you know, we are using working around missing features, I would say, right, which are available in D. And we should add more examples because I think this is a great way to learn about these things. Because what I usually do is I check out some Python code to have some idea what they are doing, and then I'm kind of like translating it or something like that. We could also think about auto-generating some of the code that is currently written by hand. It's a nice way of doing, I think. The tape-based gradient calculation, I've talked about this autograde API. We could integrate this. And we could also make use of uniform function called syntax, which would you give something like this to define your network, which looks more pleasant to me than the Python API. So conclusions, yeah. So I've shown you I could say like an integration of a very unpopular deep learning library called MXNet. It's unpopular. I can say still it works. You can use it. And we have this integration, and you can essentially make use of it. So feel free to check it out and yeah, play with it. All right, that was it. So thank you for your attention.
No questions? Oh, one question. All right.
Some math question. Ben, do you hear me? Math.
So you're developing this, well, I think it's sort of an integration. You're writing a D wrapper for the MXNet library.
Yes.
And what are you actually planning on using it for?
So the company has data, and we apply it on the data. So the bottom line is, I do not know like how far or how deep I can go into the details, like what it's actually doing. Yeah, no, I cannot say more. But you know, if you want to apply it, find your own data and just build something, right? That's how they do it. Yeah.
And just one more thing. So the reason you're not simply using the C API is because you want to write it in D because it's nicer looking and more easy to understand, or?
No, that's good that you ask us. No, so to clarify, the reason is more like if you go with like TensorFlow, you would have like a divide in your like I would say prototype production setup, because essentially you would do the prototyping, also training of the model in Python, and then you would somehow write out the model parameters and now integrate them into your production system, which maybe isn't Python. Or you would need to write out something. At least there would be some bridge, some gap to bridge. And so if you have it all in D, you just have the same code everywhere, and this makes it at least from this perspective, less of a problem. So I do not know like how much of a problem this actually is. You can have both approaches. And I think there's always a reason for like going with the existing one, because you know it's well established. You shouldn't run into many problems there. But yeah, so if you for whatever reason need it right into the language, because let's say you want to apply it in real time, then you may want to use this. Yeah. Other questions? One other.
What if you want to use some of the typical tools like, I don't know, Jupyter, or integrate this DMXNet with?
Yeah. So Andre was posting the other day this this framework, what's called Grain, and they build like a Jupyter kernel, right? They built, I don't know how this Jupyter thing works, but they built something to make Grain available within Jupyter. So there is some kind of, somebody from Symmetry was actually doing this, right? Yeah, so there is some support. I do not know how this works. I haven't looked into it. But I get that somehow you can integrate D-code, like you build it, and then you can make it available within Jupyter, essentially by providing a D kernel. So I think you can do the very same here. I do not see why you shouldn't be able to do this. Also note I was using something like a Jupyter thing here, but I was like a bit hacky. So yeah, it was similar. It actually was a Jupyter notebook, but I was like mainly like writing files there and was not that well integrated. But yeah. So there's somewhat an integration. I haven't looked into it. Definitely, like, would be a good contribution. All right. Thank you.